Last chapter, we talked about the binomial distribution, multinomial distribution, a lot of different ones, and those were all discrete, right? We could make a little table, and we could put it in a nice little table, 0, 1, 2, 3, and then the probabilities. The normal distribution is a continuous distribution, so it's going to look very different in the fact that we're not really going to be able to put it in a nice little table. It's continuous, goes on forever, okay? And it has infinite number of points in it, so we really can't put it in the table, because if we were, we'd have to put in x equal to negative infinity, and then negative whatever number comes after negative infinity, and 1.11113 and 1.256, you know, it's got every number in the book, okay? So it's a continuous distribution, so we won't be able to put it in a nice table, but we'll still be able to work with the normal distribution and find different probabilities. Okay, we're only going to cover the first 3 sections of Chapter 6. 6.1 is called just plain old normal distribution. It's an introduction. 6.2 is the application. How do we use the normal distribution for real life problems? And then 6.3 will be central limit theorem. That's it. That's all we're doing. So like I said, it's kind of a short, sweet chapter. There aren't very many concepts. Basically, everything's just normal distribution. All we're going to use is that normal CDF on our calculator, one function. Okay, it's just how do we put it in, and for different problems, how do we apply it? I take that back. When we want to work it backwards, we're going to use also the inverse norm. So normal, CDF, and inverse norm, those are the only 2 that we'll be using. Okay, so just focusing on normal distribution, and there is a section 6.4, but I took it out. I'll tell you just quick why. 6.4 is how you can use a normal distribution to approximate the binomial. So you can use it as an approximation for binomial. The thing is with calculators, we don't need to approximate binomial because you guys can use a calculator to do infinite number of numbers with binomial. So we don't need to use normal to approximate. So we don't cover that anymore. It's kind of something that they used it pre-calculators, okay? And then that's when they were, for normal distributions, they'd look everything up in a table. We're not going to be looking up things in the table. We're going to be using the calculator. Many distributions, or many continuous variables have distributions that are bell-shaped, okay? So as we get very large populations, we're going to look at continuous variables, okay? That's why I said it's not discrete. Now we're doing continuous, and they have to be bell-shaped, okay? So what I'm saying is if we were to make a graph, the graph cannot go up, down, up, down, up, down. It's got to somewhat kind of just do this, okay? And there's our nice little bell curve, right? So we've seen this before. And as you look at very large populations, guys, it almost always ends up doing this. If we were to look at everybody who tested on the ACT, okay, it would do like this. There would be a few people that scored super low, like a 10 or something. There would be a few more that would score in here. The average for the state is like 20, 21 or something like that. I don't know. Yeah, I was going to say 20, 21, 22, somewhere in there. So that would be in the middle, okay? And that's where most of your people would be. Then you have a few people scoring higher, and then you have that very small percent that score what? 35, 36, right? So it looks like a normal distribution as you look at the entire U.S. Okay, maybe Iowa is a little bit skewed one way or the other, but as you look at everybody, it's going to look like this. As you look at the heights of everybody in the world, okay, it's going to follow this normal distribution. You're going to have a couple full adults that are super short, okay? You're going to have some that are super tall, Yao Ming, right? But most people are going to be right at this middle, and it kind of does this, okay? So in statistics, they use the normal distribution a lot because with very large populations, everything kind of tends to this normal distribution. That's kind of how life is, okay? And so it says most things, many things have this, or what we call approximately normal. So if they're pretty close to this, we can use a normal distribution to do our statistics. We use a theoretical curve called the bell curve. They also call this Gaussian. It's called the Gaussian curve, I guess named after, I think his name is Carl Gauss. But this is, the normal distribution is the same as a Gaussian. I'm never going to refer to it as a Gaussian. I'm just going to call it the normal distribution or the bell curve, okay? So those are all synonyms. Normal, Gaussian, bell, they're all the same thing. And we can use them to study many variables that are not normally distributed, but that are approximately normal. So if it's close to this bell curve, we can use a bell curve to kind of figure out what our statistics are, what our probabilities are, okay? So that's what we'll be. Here's a kind of a cool thing. If you type this, which is kind of crazy, if you type this into your calculator, into the y equals, you will actually get a normal curve. Now, you're going to have, for E, you're going to have to use the E on your calculator. For mu, you would have to actually use a population mean that you knew and a standard deviation, and this will actually give you the bell curve on your calculator. You don't have to ever graph this. But I left it in here because I thought some people are kind of interested on how that curve is actually created. If you actually want to graph the curve and look at that curve, you'd type this in. Okay? Now, for sigma, you actually would have to type in what your population standard deviation was. Okay, and x needs to just stay as x. And E is actually just a number, it's that number, but there's an E on your calculator that approximates that out to further. And pi, we all know, is approximately 3.14, but you could use the pi button on your calculator. And it will make this curve. Now, you'd have to adjust your window based on what these things were, but it'll make that perfect kind of bell curve looking thing, okay? So that's just a formula behind it that does that. We're not going to use this to calculate anything, okay? This is not helpful to actually calculating probabilities. It just gives you the actual picture. Okay, so for normal distributions, the shape and position of the normal distribution curve depends on two parameters. What are the two things that are very important that we're going to need to know for every problem? The mean and the standard deviation. That's why I said at the very beginning of class, very beginning of the semester, that these two parameters are really our most important two. And ironically enough, or no, conveniently enough, our calculator, what's the first thing it gives us if we have raw data, one variable stats, it gives us the mean, right? And about 4 lines down, it gives you the standard deviation. Okay, and on your calculator, if you ever want to find mean, remember that the mean is just that x bar. So I'll just write that in here. Mean is your x bar, and that is actually the same as the population mean. You do need the population mean for the distribution, but those are the same on your calculator, okay? And then the standard deviation will be that sigma, okay? Because we're going to use the population standard deviation, that's sigma, or sigma sub x, right? Each normally distributed variable has its own normal distribution curve. Okay, so would the ACT curve be lined up exactly with the heights in the US? No. ACT curve, the middle of the bell curve is going to be at what? What do we say, like 20, 21, 22? And for heights in the US, the middle of the bell curve might be, I don't know, 65 inches or something like that, right? I don't know what they would be. So, or for average salary of people in the U.S., that's not going to be even a number between 1 and 100. That's going to be in the thousands, tens of thousands, right? Okay, so every distribution looks a little different. As we look at this, you could have, these are two distributions that have an average of 0, okay? This top curve has an average of 0, but the standard deviation is only 1. Okay, and that's our normal distribution if we put it in terms of standard normal, a z-curve, z-score. So that's kind of the standard one, but then this one has a standard deviation of 2. So it's a little bit lower and it's more what? Spread out. Do you see it? So every distribution looks a little different, but they all look approximately normal. They're all bell curves. So we'll be able to use the same function for all of them. Now these two populations, this one has an average of 0, this one has an average of 2. So see, they're in two different spots? But they have the same standard deviation, so they have the same spread outness. So if they're just comparing and they're saying that basically no matter what distribution, no matter what set of population we have, every curve is going to look just a little different, but they're all going to be bell curve. They're all going to have that peak right in the middle, okay? And they're all going to be perfectly symmetrical. So it doesn't matter what our mean is and what our standard deviation is, they're all going to follow the same picture that we have. Okay, so let's go through all the properties of a normal distribution. Do we know the first one? A normal distribution has to be bell-shaped. Do we know that one? Okay, check. We know that one. All right, so we've already talked about that. I don't need to go over that again. The mean, the median, and the mode are equal and located at the center of the distribution. Does that make sense? It's totally symmetrical, that the mean, the average would have to be right in the middle. The median, if you lined up all the numbers, the middle number is going to be the middle, right? And then the mode is the most frequent. Wasn't that the highest part of our peak, right? So that one was the most. So mean, median, and mode are all equal. Okay, check. The normal distribution is called unimodal. Unimodal as opposed to what? Bimodal? Yes, bi would mean two modes. Unimodal means one mode. That means it just has one bump in it. Okay? Unimodal means it just has the one bump. You guys know una means one. Okay? The curve is symmetrical about the mean. This is very important. That means it's perfectly symmetrical. So there's the same amount of things on this side and this side. And when you fold it, it should match up perfectly. Okay? So now I know not every distribution is perfectly symmetrical, but if it's approximately normal, we're going to assume that it's symmetrical. So the curve is symmetrical about the mean, which is equivalent to saying that its shape is the same on both sides of the vertical line passing through the center. So that's our symmetry line. Okay, there's our symmetry line from geometry, right? Or our axis of symmetry. And everything on this side matches with everything on this side. Now, my picture's terrible. It doesn't look that way, but it's supposed to. So here's my question to you. What percent of the numbers land on this side? What percent? 50, yeah. What percent land on this side? 50. Okay, right? Obviously, if the median and the mean and the mode are all right in the middle, 50% is on this side, 50% on this side. It's exactly the same, guys. 100% of the data values lie in that curve. Okay, this graph. Okay, this one is kind of interesting. The curve is continuous. What this means is there are no gaps or holes, and for every value of x, there's a value of y. Okay, for every value of x, there's a value of y. That means this graph is continuous, perfectly continuous. Now, in reality, when you collect data, is any set of data perfectly continuous? No, okay? Because we can't find infinite number of numbers. No statistician is going to collect infinite number of numbers, right? But you have to go in theory now. When we're looking at that, and theoretically, in theory, this normal distribution is going to have infinite number of numbers we should be able to calculate for any value. So for any x value, there's a y value. That means that this curve right here, guys, has no breaks, no holes, no jumps, nothing, okay? So it's totally smooth, totally continuous. And here's the one thing. For every value of x, there's a corresponding value of y, which means this. It's going to tell you in just a second. It never touches the x-axis. Okay? So here's my x-axis. And theoretically, so in theory, no matter how far you go in either direction, it extends, never meets the x-axis, but gets increasingly close. So I should technically put arrows on the ends of both of this. It goes on forever in either direction. It never meets the x-axis, but it gets increasingly close. It gets so close that the difference does not matter. So ultimately, once we get like 5 standard deviations away from the mean, basically it's nothing. It's pretty much touched the x-axis. It's so insignificant that we don't really care about it. But I need you to understand that in math, we have to always think of in the big picture. In theory, it goes on forever, right? And that's kind of like in geometry. In geometry, when you first learn about what a line is, in theory, a line goes on forever. Is there any line on this earth that actually goes on forever? No. Everything has a start and a stop, right? Okay? Is there any plane on this earth that goes on forever? In geometry, a plane is a flat surface that goes on forever. No. Every flat surface has an ending point. It stops, right? Okay? So this, again, is in theory. It goes on forever. But, guys, eventually it doesn't really matter what's out here. So we only look at, certain pieces of it or whatever. But we're going to use negative infinity and positive infinity. And what I want you to know is if we're talking about forever going this way, this would be our negative infinity. Okay? Because this is to the negative side. That's the infinity symbol. And this side is positive infinity. Now, if we are talking about everything less than a certain value, we're going to use negative infinity. Everything greater, we're going to use positive infinity. Even though we know technically, like, it doesn't go any higher than Well, you can't go to infinity, okay? That's fine. We're going to still put infinity in our calculator because after it hits about 500, it's going to not matter. Now, do you think your calculator can hold the number infinity? Can our calculator actually hold the number infinity? No. The calculator also has limitations, right? But again, we're never going to go out to 50 billion decimal places, right? We're only going out to 4. So the calculator does hold way more than 4 decimal places. It holds way more than 8 decimal places that you see on the screen. It actually understands, because have you seen it where it does the E50, E12, right? It puts it in scientific notation that it actually understands up to 99 decimal places. Okay? So what we're going to use for negative infinity is negative and then an E and then 99. And what this does is this is actually going to negative infinity, okay? This is 99 decimal places with a negative in front of it, okay? And really, I don't have to put the 1 here, but it's 1 with 99 decimal places and then negative. So it's a 1 with 99 zeros after it and a negative. Sorry, not decimal places, zeros, 99 zeros. So I'm not sure what number that is because a billion has, what, 9 zeros? I'm not sure what number has 99 zeros, but your calculator can understand that, okay? And then for positive infinity, that's going to be what? E99, right? So negative infinity is negative E99. Positive infinity is E99. That's a 1 with 99 zeros after it, okay? So 1 quadrillion, billion, zillion, million, billion, infinity, whatever. Okay, I don't know what the number is. I have no idea. I don't know if there's a name for it. Google it. I don't care. I have no idea what this is called. So that's what we're going to use for our values for negative infinity and positive infinity. Okay, the total area under the normal distribution curve is equal to 1. So if I were to think about it in terms of area, the area under a normal distribution curve, we call it is 1. Or what is that in terms of percents? 100%, right? Okay, so if we're graphing all of our values, how much area is under there? 100%. The area under the normal curve that lies within 1 standard deviation of the mean is approximately 68%, 95% for 2, and 3 is 99.7. Review. Do you guys remember this? This was the empirical distribution, which was for normal distribution. So we've already talked about this. This was the empirical rule. All right, so here's our normal bell curve. Reminder that about 68% are about plus or minus 1 standard deviation from the mean. 2 standard deviations, you're going to hit 95%. 3, you're going to hit 99.7. So once we hit 5 standard deviations, guys, we've hit basically 100%, okay? Not really, because it goes on forever, in theory. That's why I don't have that. That's why this says 0.13% is for everything out there, okay? But you got to understand that this keeps going forever and ever and ever. So technically there should be an arrow here and an arrow here because this curve goes forever each way. But the total area, because it gets increasingly close, is 100%, okay? So there's 100% under that entire curve because that's all of the data values. All right. What's the difference between the normal distribution and what we call the standard normal distribution? Okay, so all of data that we collect, a lot of data, it kind of fits that normal bell curve, okay? But sometimes the mean is in different spots, right? Sometimes the mean is for ACT scores, it's in the 20s. For heights, it's in the 60s, whatever. So the mean is in different spots. The standard normal distribution always has a mean of 0, and the standard deviation is always 1, okay? So it's standardizing it and looking at that picture. So if I go back to that very first slide, if we were to make a picture of it, we would want the mean to be 0, the standard deviation to be 1. And this has to do with our z-scores. We did z-scores before, so we're going to bring that into it a little bit. So a standard normal distribution is a distribution with a mean of 0 and a standard deviation of 1. And in other words, if I take something and make it a z-score, and you were average, Remember when we did averages and you were an average height? What was your z-score? It was 0, right? When you were average? Yeah. And so the z-score of 0, that means the mean is 0. That's right in the middle. And then your standard deviation is 1. So if we're 1 standard deviation away, we're exactly that picture that we were just showing, okay? So this is positive 1, and this value is negative 1. And then 2 standard deviations away, so there's positive 2 and negative 2, and then 3 is negative 3 and positive 3, and then there is still more after that, but that pretty much hits our whole curve. So this is the standard normal distribution, that this value be 0. If you're below average, right? If you're below average, what's your value going to be? It's going to be negative. If you're above average, you're going to be positive, right? So where did these numbers come from? I want to remind you, these were when we were doing the z-scores. So a standard normal distribution, the standard is to actually put everything in terms of a z-score. Now here is a little bit of history. Old school statistics, you had to change everything to a z-score. And then they had a chart in the back of your book, which is still there, with all these numbers that tell you, okay, if you land here, everything from here less, this has this area. And everything here less has this probability and this here. So you had to change. Every time you wanted to do a problem, you had to take the data values and change them into z-scores if they weren't already z-scores. That was kind of a pain in the butt. And then you have to look it up in the chart. In the very first year I taught stats, we didn't really use the graphing calculator very much because most people didn't have them. And that's how we did every problem. In chapter 6, believe you me, took us about 3 weeks, okay? Because of the cumbersome annoyance of trying to explain, get everything into a z-score, and then trying to look up these charts and read the charts and understand how it worked. Now I can do it in about 2 days because of the ease of using the calculators. So these charts have gone by the wayside, and the charts are only accurate out to 4 decimal places. Our calculator, as we know, can be accurate out to 99 decimal places. So we kind of have gone away from using the standard normal distribution, but you still need to understand that that's what everything can be standardized to this distribution by just changing it into a z-score. Okay, yeah. So how do we find our z-scores again? We take our data value, we subtract it from the actual mean, population mean, and we divide by the standard deviation. That changes it into a z-score. So if you are average, these two numbers will be the same. You'll get a z-score of 0. If you're above average, this number is going to be bigger than this, so your z-score is going to be positive. If you're below average, your z-score is going to be negative, right? Because this number will be smaller than this number. And reminder, if you're ever going to change something to a z-score, you don't want to type it all in one line. Make sure you put parentheses around that top stuff because all of that is being divided by the standard deviation. Okay. Okay. Here are the 2 things that we're going to be using. We are going to be using normal CDF, and I put here to find the area, okay? The area, and the area is the same as the probability, guys. We can change this into the probability. The probability or the area under the curve. You use normal CDF, and I abbreviated norm. I think it's actually the full word normal, isn't it? Is it just norm? Yeah, it's normal. Sorry. I always just call it norm CDF because I think I just abbreviate. This is actually on your calculator. It's normal CDF, and it is lowercase. So let me just get this in here right. Normal CDF. And then you put in the low z-score, the high z-score, and then the mean and the standard deviation are always going to be 0 and 1 if you're using a z-score, okay? For z-scores, that's what we have. So this is for standard, for z's. Then, if you don't want to change them into z-scores, or if you don't have z-scores, you just put in your low x value, your high x value, the actual mean, and the actual standard deviation in the problem, okay? And remember, the mean is mu, standard deviation is sigma. I'm just going to keep using those letters. So that's the order in what you type them in. It's always low, high, mean, standard deviation. Low, high, mean, standard deviation. Okay? And I did put on this slide again, negative infinity. We're going to use negative E99, positive infinity, E99. Let me show you how you do that on your calculator quick. Negative infinity, okay? The way you type that in is you actually have to use the negative button down here. So negative. And then E is actually, it's a double E on here, but it shows up as an E. It's on the comma button. So second, comma, and then it will just be an E, and then 99. That's how you would type in negative E99. Okay? And then if you want, if I hit enter, it's just going to call it -1 E99, but you don't have to put the 1 in. And it knows that this is a -1 with 99 zeros after it. So that's as close to negative infinity as I can get. I don't know how to get any closer. And then it will also take positive E99, so second comma and then 99, that's positive infinity. Okay? So that's the biggest number it will hold. Okay. I'm going to just write that in here. It's the second button and then comma. And then that will give you the E. Okay. All right, so let's do our first example. Area under the curve, okay? Find the area to the left of z equal to 2.09. This is asking the same question as what's the probability, okay, that z is less than 2.09. And since it's continuous, I don't need to worry about if I can put less than or equal to. It doesn't really matter, guys, because at this value, there really isn't any area. So yeah, I can put less than or equal to. This is the same as what this is saying here. What's the probability that my z-score or that any value would be less than this? Or what's this area? Or what percent is in this part? It's all asking the same thing, okay? So how are we going to set this up? Let's write down our steps. It's going to be normal CDF. This is a normal distribution. Why are we doing CDF? Because it's cumulative. We're never going to be doing PDF. Okay, we're accumulating. We're doing a running total. So it's a CDF of, okay, what is the lowest value on this graph? To the left of 2.09. It's not 0. It's what? Negative infinity. Okay, so since this is shaded all the way over to here, it's actually this value way over here is negative E99. Okay, so we're going from negative E99. What's the high value? Highest on this graph up to 2.09, right? Comma. The mean and standard deviation. Ms. Tapper, this problem didn't give us the mean and standard deviation, so let's leave it blank. No, if it's a z-score, the mean is always 0. Standard deviation is 1. That's the default, guys. If they don't give you a mean and standard deviation, it's a z-value. Mean is 0, standard deviation is 1. Okay, so my question is, what's the probability that you're going to be a 2 or lower? What area is this? Okay, type it in. What percent of our data do we have? 0.9816911,644. And those old school tables only give you out to 4 decimal places. On your calculator, you can see out to, what is that, 10 decimal places? Let's go out to 4, okay? So 0.9817 is what I got. Does that sound good? Okay, so what would that be as a percent? 98.17. 98% of the data, guys, is from 2 standard deviations or less. That covers 98% of your numbers. All right. Okay, here's your next one. Find the area to the right of this. So from negative 1.14 to there, write it. Apply the knowledge that we just used. Now here's the cool thing. I know it's a running total. CDF is that, but you can actually tell it the low and tell it the high. So what are we going to put for low? Yeah, this number is going to go in first. That's the lowest on our graph. That's furthest to the left. Okay, Ashley, do you have an answer for us? 0.8729 to 4 decimal places. Okay. Verification, that looks good. Yeah, okay. What would happen if instead of E99 right here I put a 5 in? Because I know that you guys, I knew that like after 3 standard deviations there was hardly anything left, and after 4 there's got to be like nothing. And what if I just, instead of putting positive infinity, if I just put a 5 here? Just try it. Go back and change that to a 5. How close is it? Rounded to 4 decimal places? Is it still that? So theoretically, just always to be safe, we just go to E99, okay? Some of the real life problems, you guys are going to say, well, does it make sense to go to positive infinity? It stops here. And I'm going to say, you're pretty much going to get the same answer, okay? But because we're doing this in theory for all values, we really do want to put in this E99, okay? But I just want you to understand that, yeah, there's nothing really left after 5, right? There's very little area. And so when we're only going out to 4 decimal places, yeah. Okay? All right, next, quickly do this. Some of you maybe already looked ahead and done this one. Go ahead and do it. I'm going to call on someone. Okay, so this is between these two values. So you won't have to use an infinity. That should be easy to type in. This is, again, the same thing as saying the probability that z is between 1.62 and, negative 1 point. There's missing a decimal point here. This is not negative 135. This is 1.35. So probability that, this is the probability that z is between negative 1.35 and 1.62. Okay, let's go with Stephanie. Is she there today? Okay, here you guys. Stephanie, are you there? We can't.
Yeah, sorry, I couldn't read that very well.
Oh, okay. There you go. This is negative 1.35 to 1.62.
.8589.
Okay, so this is the area in here. Okay, 85% land between here and here of all data values. Okay. All right, so you have 3, and now they set them up in these little things. They didn't give you a picture. Okay, so I'm kind of testing you. So I want the probability that z is between 0 and 2.53 for letter A. This one's the probability that z is less than 1.73. Or I can put equal to's on any of these. It doesn't really matter. Okay, so you don't actually do a number lower than this. It's less than or equal to, or is less than, because that value is just kind of my cutoff. And then greater than or equal to 1.98. You don't need to go to the next number up. Okay, so it's fine. It's the same. It's going to be the same thing if I put this here because it's continuous. All right, so go ahead and calculate those 3 out. Write in maybe your work so you know what you're doing, so you remember how to do it when you get to your homework. Emily, you're up for letter A. Wesley, you got letter B. And Hannah, you have letter C. And even if I didn't call your name, you should still be working on them. If you have to, think about what your picture would look like. Whenever you have them done, go ahead and share out. Hannah, go ahead. And what did we use for our low? High? Yep.
A, I got 4943.
0.4943. And that one, you got your low and high right there, so that one was easier, probably. 0, 2.53, 0, 1. Okay. How about for B?
For B, I got 0.9582.
Okay, and what'd you use as your low?
The low was negative E99.
Mm-hmm. Okay, because it's everything less than this, so the lowest is going to go as negative infinity. And then all the way up to 1.73, comma 0, comma 1. How come this one was such a small percent? Because it's at 1.98 above. That's a really small part of the graph, right? And this one's almost the whole graph, 1.73 and below. And this one is about 50%, right? Okay, because we're going from 0, the middle, to 2.5. And 2.5 is at the very top of the graph. Okay. Okay, so here's the next question. Find the z-value such that the area under the standard normal curve between 0 and the z-value is 0.2123. What are they giving us? This is the answer, right? Okay, so you're going to sit there and guess and check until you get the number that works. I mean, you can. I could be mean. I could say, I'll just sit here and wait till you guys find the number. Start typing it in. Norm CDF, 0, comma, pick a number, and comma, 0, comma, 1, and till you get that number. Who's my good guessers? Well, we knew 2 point whatever was up here. One standard deviation that was like 34%, wasn't it? So it's less than 1. Who's got a guess? 0.8? 0.7? I don't know. Something positive, right? Okay, so there has got to be a method, right, to be able to work this backwards. So we're using a function called normal CDF to create and to find the area between under the curve without having to do tables. There is one method that you can do. You can actually go to the back of your book, look this up in the body of the table, and then you have to go out and find the z-score. Better yet, okay, is you just do this. We're going to do inverse norm. Why do you think it would be inverse norm? Because we're doing it backwards, right? We now have our answer, and we want to find the actual z-value. Now, let's go to our inverse norm function on here. So if I go under distributions, it's actually the third one down. And if you have the old school calculator, it doesn't tell you these things, but the first thing you have to actually type in is the area. Now, the area, you need to listen closely. the area you are going to type in is the area that is to the left of the value that you want. And then you always put mean as 0 and standard deviation as 1. So I'm going to put the general rule here. And you need to put this in your notes somewhere because I don't want to have to continue to keep saying this. For inverse norm, it's the area, the total area that would be to the left of the z value or the x value, okay? And then comma, 0, comma, 1, okay? So the total area that's to the left of this value. So inverse norm actually does use the running total, so it needs to know what is all of this to the left in order for it to give us this one z value, because you don't get to give it two values, okay? So you have to tell it how much area is to the left of this value. Well, let's look at this picture. 0.2123 is in here. How much area is to the left? Well, how much is in this space here? 50%, right? Has to be. This is half the curve, right? So 0.50 is here, or 0.5, and this is 0.2123. So what number should we type in first into our commands? Total area to the left is how much? 0.7? 1, 2, 3, right? 0.5 plus 0.2123 gives us a total area. This whole thing is 0.7123. So we're going to do inverse norm of 0.7123, comma 0, comma 1. $56.56. This is not a percent, okay? So don't change it to a percent. This is the z value. So it says find the z value. So we need to put z equals 0.56. Now, here's the crazy thing, okay? I guessed 0.7. That was my guess. I was off a little bit, okay? But it makes sense that my answer is 0.56 because it is positive. It should be positive, right? And we're going to do another one here in a minute where maybe my z value be negative. If I'm trying to find a z value that's over here, I better get a negative answer. Now, for norm CDF, are you ever going to get a negative answer? No, not unless you type your numbers in backwards, okay? You should always get a positive number because that's an area. But for this is finding the z value. The z value can be positive or negative. There isn't one more. I'm going to pause this, okay? Applications to the normal distribution. The standard normal distribution curve can be used to solve a wide variety of practical problems. The only requirement is that the variable is normally distributed or approximately normally distributed, okay? So for all the problems presented in this chapter, you can assume that the variable is normally or approximately normally distributed. So you're just going to assume that the data actually, they're not going to state it in every problem. But technically, if you were doing research on your own and you had data that like had 2 bumps in it, you wouldn't want to use normal distribution. Okay, it's not going to work. So for all of these problems, they're approximately normal. So liters of blood. An adult has on average 5.2 liters of blood. So what number is that? When I say on average, that's the mean. Okay, so I'm going to write that down right away. Right away I know that the mean is 5.2. Okay, assume the variable is normally distributed and has a standard deviation of 0.3. What number is 0.3? Standard deviation, right? Okay. Find the percentage of people who have less than 5.4 liters of blood. Okay? So the percentage, isn't that the same as probability? Yeah? Okay? So we want, what's the probability that we have less than 5.4 liters of blood? This number, guys, this is my x value. It's not a z value. It's just a data value. This is a data point, so we're just going to call this x. So we are finding the probability that x is less than 5.4. Okay? Now remember, because this is a continuous curve, it doesn't matter if I say less than or less than and equal to. So we're going to go right up to 5.4. That's going to be our top number. If I were to look at a picture of this, just so that you all can see, it would look something like this, a normal distribution. The mean would be 5.2, so no longer 0, but it's going to be 5.2 in the middle. And if I go 0.3 to the right and to the left, that gets me about 68% of the data. And then another 0.3 out and another 0.3 out, right? So that gives me my kind of my picture. 5.4 would be on this side, right? Somewhere over here. So I'm going to just put a line where I think 5.4 would be. And I want the area, the probability, or the percent that people that have less than 5.4. Now, this is not an inverse norm one, because we're not trying to find the value. We're actually trying to find the area, the probability. So we're back to just plain old norm CDF. What's my low value? If I want everything less than 5.4, what do I put in for low? Oh gosh, Mrs. Tapper, nobody can have less than 0 liters of blood. Right, I agree. Okay. And in fact, this graph isn't going to go even down to 0 because nobody can have less than like certain amounts of blood or you're dead. Okay. But in theory, this curve goes forever, right? So we're just going to put negative E99. Now, if you put 0, you're probably going to get the same answer as us. Okay. But low number is going to be negative E99. High number is going to be what? 5.4. What are we going to put in for our mean and our standard deviation? These two numbers. Not 0 and 1, guys. Okay? You got to change them. No longer 0 and 1 because these are not z-scores. You got to use your actual mean and standard deviation. So 5.2 and 0.3. I hope you got 0.7475. Okay? If you didn't, talk to someone next to you and see if they got it and see what maybe you did wrong when you typed it in. 7475. Oh, I'm sloppy today. I think it has to do with not feeling well. Okay. I want you to try this next one on your own. Okay, read through it, pull out the important information. You got to find between 27 and 31, and you also have to find more than 30.2, okay? And again, you're finding the probability of this happening. So we're going to go ahead and be using our norm CDF. I would write down what your work is. So there's 2 parts here, okay? You're going to do part A and part B. And in a minute, I'll call on someone. Help each other out, getting them set up. You may work with someone, okay? Feel free to talk. Okay, Emily from Turkey Valley and Andrew from West Central. Emily, you have A, Andrew, you have B.
A is 0.6247.
Is that what she said?
2.247.
Transpose those. Okay. And B, Andrew?
Yeah, I definitely got the wrong number.
Can you tell me what you typed in?
Yeah, me and Jack are a little lost.
Okay. Well, we gotta be paying attention and following along with what we're doing. This is just like the last one that we did. So, more than 30.2, what's the low value? That would be 30.2. And more than that would be going to all the way up to infinity. Okay, then we need the mean and the standard deviation. Which number in this problem is a mean? Okay, Missy, can you help us out?
Wait, 1357.
Okay. Good? All right. All right, one more. This one is, you notice there's a percent in here. So, and what they're asking us is to find the lowest possible score. So what I noticed in this problem right away is this one is kind of working backwards, okay? Because they give us an area. They give us a probability. The best way to understand these guys is to make sure you draw a picture. So we're going to draw a picture. So to qualify for the police academy, candidates must score in the top 10%. Okay, so that means I have this top little 10%. So not that this value is 10%, but this area is 10%, right? Okay, so 10% is right here. All right, the test has a mean of 200. So I'm going to just throw that in the middle. That's our mean. And our standard deviation is 20. There's not really a spot to put that on here. That's not this value. That's just how far, you know, each thing is marked out. So I'll just put that over here. Standard deviation is 20. Find the lowest possible score to qualify. I want to find this score, right? That's the lowest score you can get to qualify to be in this top 10%. So we want to know this value right here. So again, how do I find that? Well, this is an inverse norm one, right? So we need the area below this one. Inverse norm, if we wrote it down in our notes, was inverse norm is area below. So what area is below this value? You got to know how much is below this. 90%, right? We know 10% is above, 90% is below. So inverse norm 0.9, comma. Now when we did it before, it was 0, 1. That was for a z-score. Now make the connection here. What's our new mean? What's our 0? What's our mean? 200, and our standard deviation is 20. So 0.9, 220 with inverse norm. And Levi, what'd you get for an answer for that?
5.631.
Say that one more time.
225.631.
Okay. I just heard the 5 and I'm like, there's no way it could be a score of a 5. So what's the lowest possible score to qualify? A 225 or 226. I don't know if you can get parts of a score on this. We have no idea, right? So what would it be appropriate to round to? I don't know. A 225, if they need a 225.6, they probably need a 226, right? We probably want to round up. To me, it would make most sense. They probably don't get parts of scores on this, but who knows? So maybe a 226. Okay? And if they get a 226, they're in. You're in your top 10%. Okay. Is this the last one of these type? And does it move on to a new kind of a...
And it goes to normal distributions. This is there a number way stuff.
Yeah. Okay, we're not going to do that. So this is our very last one today. Systolic blood pressure. For a medical study, a researcher wishes to select people in the middle 60%. Very similar to the one that I showed you that I did the middle 64%, right? Or 84%. No, 84%, wasn't it? No, 64. It was 68. 68%, whatever. All right. I don't know up from down right now. Clearly my brain's not functioning. So we want the middle 60%. If the average blood pressure is 120 with a standard deviation of 8, find the upper and lower readings that would qualify these people for the study. So the average is 120, that's our middle. And we want to know the lower and the upper, these values, if we're going to do the middle 60%. Okay? The middle 60% means 60% is in this middle. So right away, since I'm going to divide it right in the middle, I'm going to put this is 0.30, that's 30%. This is 30%. But to find these values, we need to know what? How much is below it, right? So to find this one, we need to not type in 0.30, but we're typing in how much is below this value. 0.2? Would have to be 0.2, right? For this one? For the left one? Okay. So for this one, we're going to do inverse norm. 0.2. What was our mean? 120. Standard deviation of 8. And then I want you to think about how you're going to get this top one. How much is below that to get that value? Morgan, what'd you get for our first one? Sorry, we went too fast. 0.2, 128.
113.27.
Okay. So blood pressure, I don't even think they ever go to decimal places. We'll just go blood pressure 113. I don't know, those of you who are going in the nursing field, you pay attention to that, right? 113? Sure. 113.27, but for this blood pressure one, a score of 113. That would give you, yeah. And then how about the top cutoff then? Well, since it's symmetrical, that's 7 below. I should have to go 7 above. It should be a 127. I'm just using common sense there, okay? If I want to use my calculator, what am I going to have to type in? Inverse norm. What percent is below here? Well, this is 30, this is 30, this was 20, so it was what, 80? So 0.8, 128. And we got a score of what, 127? 126.7, which could round to 127. So between about those two, again, I don't know if they want us to round down and kind of pull it in a little bit, but looks like that would be right for this medical study. They're not going to be exact, but they would want people that have blood pressures between these two values, right? Okay. So if I was going to answer it, find the upper and lower readings. The lower reading would have to be 113, and the upper reading would be 127, blood pressure. Okay, so in summary,